The recording is about to start. Yes, we are recording. And I move over to my screen, start broadcast, and that should work now, hopefully. And can you see the screen? I'm a genius. What have you been smoking for breakfast, Edith? I'm not a genius. And thank you very much, Bernardo, for your trusted services. You are a true scholar and gentleman, and it's really fantastic that we have somebody who does the attendance monitoring for me. It's really good. I love you. But I don't want this to be misconstrued, okay? No, actually, no, he won't lose the job because when it goes back into person, face to face, you still have to record your attendance. And for that, we need somebody to remind us. I better not ask any questions about Trivago. You are the Moodle, indeed. What's going to happen next year? This is a great question, Daria. I would like to know what's happening tomorrow, let alone next year. I have absolutely no clue. So, no. Well, we can try to do a little bit of inferential statistics, can't we? To figure out what's going to happen next year. Do we have an assessed practical next week? Ah, that's a good question. I'm still trying to get everything together for this assessed practical. So please watch that space. I will say something probably then, yeah, when the time is right. Oh, yeah. Actually, I had a lot of fun putting this assessed practical together. Yeah, I did. And I hope you will enjoy it. No. We do that in a different way. Okay, anyway, let's get started. Because I want lunch. And I guess so do you. So please keep yourself muted now. And what's that? Okay. So most wonderful, good after morning, everybody. And welcome to the BI 308 skills, where we carry on with our data analysis thing. And hopefully today we will look at some real data. But before we do that, let me quickly revise what we have done so far. So this session is about p-values, about data, and Poisson. Well, it's not Poisson, it's Poisson. When we come to that in a minute. Please don't forget to register your attendance, and Bernardo has very kindly again provided the link for it. So thank you very much. And here it is again. So we have talked about, let's say we have two samples, sample 1 and sample 2. And that's a very brief revision of what we have done in the last 2 weeks. We want to, so we've got some data here and data here, and we want to know whether these two samples are in fact different from each other. So that's the big question. Are they different? Are they different? And we said, we know that they are different. It's absolutely clear they are different because of the sampling error. So they are cause sampling error. So we know that they are different, but are they actually different enough for us to say, yes, they're statistically different from each other, or, well, they are different, but we can explain the differences with the sample error. So in fact, they are not really that different. And we said, because we can't compare them directly with each other, what we do for each sample, we calculate the confidence interval, in which we believe the population parameter that we are interested in, the population parameter is located. So we can calculate this confidence interval for each sample. And then we say, what we do is we, instead of comparing the samples, we compare the populations. Compare populations. Because we make an estimate and say, okay, this is the, say, the population mean of the predicted population mean. So this is our population mean for population 1. And this is the predicted population mean for population 2. And now we say, if they are, we basically ask the question, are they the same? Or are they not the same? Data. The question mark is data. So this is what we are basically saying. If the two population means are the same, then we can conclude that the two populations are similar or pretty much identical. And we can probably say sample 1, that's sample 1, and sample 2 could come from the same population. From the same population, because we can't really distinguish between population 1 and population 2. So we have mu1 equals mu2. We know that this is, thank you very much, mu1 equals mu2. Sorry, typo. And this is also our null hypothesis. And that is what we always start with. And we can formulate also the alternative hypothesis. As I said, mu1 is unequal to mu2. And if that is the case, then we can say S1 and S2 come from different populations. So they don't come from the same populations. And any difference that we see is between S1 and S2 is due to sampling error and an additional factor, which we might not know at that time, but which is definitely worth investigating. So we said what we do is we can actually compare confidence intervals. So here we have the confidence interval for sample 1. And let's say we have the confidence interval for sample 2. And we have this confidence interval. So we have these two confidence intervals. So from sample 1, we calculate this confidence interval. From sample 2, we calculate this confidence interval. Okay? Would you say that, so I write this as CI1 and CI2 to distinguish them. Would you say that the population means for these two populations, population 1 and population 2, would you say that these two confidence intervals are different? Are they different? The way I've drawn it? No. That's pretty obvious. Yep. They are not different. So these two confidence intervals are not different. And therefore we can say probably mu1 equals mu2. The two population means are the same. And therefore we can say sample 1 and sample 2 are likely to come from the same population. From the same population. There's a slim possibility that we have two different populations, but we can't distinguish them. Okay, how likely do you think, how likely is it that they come from the same population? Very likely, a little bit likely. Absolutely right, Edith. Very likely. So we can say, what is the probability that they come from the same population? What's the probability that they come from the same population? What do you think? Pretty high. I haven't told you what I mean by probability. Probability basically tells us how likely something is. What is the probability of doing something? And the probability can always only be between 0 and 1, or you can express this as 0% to 100%. 0% means it cannot happen. 100% means it will definitely happen. So here we probably get a very high probability. You are absolutely right. So this is the probability that we get a very high probability that the two samples come from the same population. Okay, let's do S1, S2. We have our confidence interval 1. And we have here our confidence interval 2. How likely, what is the probability that these samples come from the same population? It is. It's an interesting point that you make, because it's not 25%. Okay, coming back to that. Is it likely? No, it's not likely. It's very unlikely, because this one here says the population mean from which the sample was drawn is somewhere in here. So pop mean, mu1, is somewhere in here, whereas this one says the population mean is somewhere in here. And since there is only one population mean in one population, these two confidence intervals don't overlap, and therefore it is fairly unlikely that they come from the same population. So very unlikely. Very unlikely that they come from the same population mean. How are you going to work out the probability? That is a very good question, and we will come to that. Is it impossible that they come from the same population mean? Absolutely right. It is not impossible, because don't forget, this is our confidence intervals are just estimates. We believe that we are in this confidence interval for our estimates. But we could, and we have a 95%, so we have a 95% chance that we are right, but we still have a 5% chance that we are not right. So it's not impossible that they come from the same population mean, but it is not very likely. If you increase the confidence interval, then you would get a larger confidence interval, and you might see that, all of a sudden, it becomes a little bit more likely. Absolutely right. Very nice observation. So it's not impossible. And if we give it a value, we can call this probability, we can call this a p-value. A p-value is the probability that we make this observation, of the confidence intervals assuming that the two population means are the same. And that's sort of the definition. We make this observation assuming that the population mean is the same. Now, if we get this p-value, if we can calculate this p-value, and we find it's very unlikely, then we can say the two population means are not the same. Yeah, I think Edith, you got a few people really anxious here, but don't worry about it. So p-value tells us what the probability is. What probability is that two samples, if you think about it, that the two samples come from the same population. Same population. Or in other words, that the observed difference between the samples is just simply due to sampling error. It doesn't, yes, you are right, but it doesn't increase the chance that the populations are the same. It increases the chance that we think the populations are the same, right? There's a huge difference. It's not necessarily that they are the same, but we think that they are the same. Right. So where would you draw a line? What about S1 and S2? If we've got something like that. Is it likely that the two samples come from the same population in a case like that? Is it likely? Potentially likely, yes. That's a very, very good. There is an overlap. So we can say, well, there is sort of, yeah, oops. Hang on, what's going on here? Good, we are back. Are we still in business? Yeah. Okay, hang on. And I've got something weird going on, but never mind. Yes. So what is the probability that they are coming from the same what do you think? What is the probability that they come from the same population? Here. Give it a value. What do you think? 50%? Yeah. So 50%. 60%? Something like that. Okay. Would you say they come, therefore, from the same population if it has a 50%? Okay. So what you're doing is, where is your cutoff actually? When do you actually say they are from the same population? What is your percentage in cutoff? Would you say they have to have a 50%, at least 50%, to come from the same population? Where is your decision? They have to have a 95% similarity. That's very high. At least 70%. So they have to be at least 70% similar, what you're saying. They have to be at least 70% overlap so that we say they come from the same population. And that's a very, very high value. In fact, this cutoff point, the cutoff, and we call this cutoff point, we call this alpha. This is also called the significance level. And we can set it where we want. We can say, well, we need them to be 50% similar. Then we say they come from the same population. And the great thing is, we almost by default already set the significance level, because there is the rule that alpha, the significance level, equals 1 minus the confidence interval level, or let me call it like that. So if we say we want a 95% confidence interval for our samples here, then our alpha that is alpha, the Greek letter alpha. Then if we say we want a 95% confidence interval, then our alpha is 1 minus 0.95, and it would be 0.05 or 5%. If our, and this means the implication of that is, if the p-value is larger, p-value is larger than alpha, then we say there is some chance that the two samples come from the same population. Two samples are from same population. If the p-value is smaller than alpha, then we say it's very likely that the two samples are from different populations. So in this case, if the p-value is smaller than alpha, we would say our null hypothesis, mu1 equals mu2, we have the same population, is not correct. And instead, we would accept our alternative hypothesis. In the case of p-value larger than alpha, so in this case, we would say, yes, our null hypothesis is all right, we accept that. And our alternative hypothesis is not correct. That goes out of the window. So p-value, this p-value, this probability value, is a decision-making tool. Decision-making tool. And if this p-value is lower than alpha, then we throw out our null hypothesis. No, it was not incorrect. It was absolutely right. If you say, for example, if you go back to that here, you say, well, the p-value here, let's say p-value of this one here is, say, 50%, however you calculated that. And we had 95% confidence intervals. So this means our alpha would be 5%. We would say p is larger than alpha, and therefore we say, yes, we believe they could come from different, they could come from the same population. from same population. So it's likely that they come from the same population. So this p-value tells us what we should believe in conjunction with this significance level. No, you should not mess with a p-value. You should not round it in this case, because if you are very close to the decision point, then you easily get close to it, and that is not a good thing. So the p-value tells you whether you should believe that the samples come from the same population or not. If the p-value equals alpha, which usually won't happen because of the maths behind it, it will usually not be 5% exactly on the dot. But if it is alpha, then the usual thing is to say, no, I'm not entirely sure that I accept the null hypothesis. And we will discuss that in a minute, how we work out alpha. So alpha is a decision-making tool, nothing else. And there is a very easy way to remember that. If P is low, that means if P is lower than alpha, if P is low, H naught must go. We reject the null hypothesis and we say the two samples most likely come from two different populations. If P is low, H naught must go. If P is high, higher than alpha, if P is high, H naught, and now I need to use my best Australian accent. If P is high, H naught can die. We say, yeah, H naught is okay. I'm not Australian, so it's probably horrible. Just sounded German. I apologize. But this is how people remember it. If P is high, H naught can die. If P is higher than alpha, we accept the null hypothesis. So this is the basic of inferential statistics. And if P is larger than the significance level, we believe in the null hypothesis. If P is lower than the significance level, we say the two samples definitely, most likely, come from two different populations. And they are different. Now, you probably have noticed, yes, H naught is the null hypothesis. That's why the naught is there. You've probably noticed that I have not told you at length how we actually calculate the confidence intervals. How to calculate the confidence intervals. And there's a reason for that I haven't told you explicitly how to do that. The reason is that your confidence interval depends on what kind of data you have. What kind of data? This determines how you calculate the confidence interval. And this then determines how you compare the two populations. So what we could have is, in terms of data, what are our observations? So for example, we could have nominal data. And you've done that in GCSE maths. So nominal data or categorical data is pretty much the same, where you just simply have things ordered in categories. So male, female, non-binary, for example. This would be 3 categories. Dogs, cats, tortoises. These are categorical data, and you usually have counts in there. So these counts would usually be sort of discrete data, discrete observations, and I abbreviate it like that. On the other hand, you can have what is called continuous data. Continuous data. So for example, when I weigh my dogs, the weight would be continuous data because there is, depending on the scales that I use, it would be, the dog, what does the dog weigh? 42.38 kilograms. Or tomorrow, the dog weighs 42.05 kilograms. So here the data are continuous. There is not a discrete point. They can be anything in between a certain range. And that's very important because that has an implication on how we, for example, determine the confidence interval. Sounds incredibly esoterical. Let's work with an example. And the first example that I want to do with you deals with count data. It deals with count data where we count observations. And we want to compare 2 observations with each other. Now, under certain conditions, we can use some equations or what is called a distribution for these things, which is derived, or which was derived from a French mathematician by the name of Poisson. And that's why the whole thing is called a Poisson distribution. Very often this is totally neglected in teaching. Why? I don't know, because in my opinion, this is one of the most important techniques. Yes, Poisson means fish, indeed. He came up with the maths for this distribution. What does this distribution look at? What are these count data? The count data are actually observation of something happening, of an event in a time span, or space, or even as a ratio, let's say. What do I mean by that? The classic example is number of calls to a call center per hour. So number of calls per hour. Or number of shark attacks per year. It was actually derived with the example, how many people are killed every year in the Prussian army through kicks from horses. This would be exactly a Poisson distribution, the number of calls to your phone per hour. So it could be 0, right? And that would be that would follow most likely a Poisson distribution. Space, it's not span, it's space, or even a ratio, and we'll come back to that in a minute, what I mean with that. Important for a Poisson distribution is the events are independent. Events independent from each other. So if you call into a call center, one caller does not know or does not react if somebody has previously called. Events are independent. Events are random. And usually the events are potentially unlimited. So, for example, if I want to look at how many people in a nightclub go to the toilet in a certain amount of time per hour, how many people in a nightclub or in a bar or in a pub or in a restaurant visit the toilet within 1 hour, would that follow a Poisson distribution? If I look at how many people go to the toilet per hour, would that follow? Yes. We have observations of event in a time span. Yeah. Oh, so yeah. Actually, not quite. If you are male, this would probably follow a Poisson distribution. Going to the toilet in a restaurant. If you are female, at least that is my observation, it would not follow a Poisson distribution because they usually go in batches. Women travel in packs. Lucy, exactly. And I don't mean this in a sexist way. It is just simply my observation. They go in packs. So it would not be independent from each other, the events, and therefore it's not sort of a Poisson distribution. Safety in numbers, absolutely. Now, let's have a look at something that has recently been discussed in terms of Poisson distribution. And that's something that obviously for me is, Hassan, don't ask, right? Don't ask. There are certain things that we don't understand. But something that is of huge significance for me. And I need to go to my photo library because I want to show you that. And if I find it. Yes, I think this is the one that I want. Yes, that's the one. Our Prime Minister made an announcement on Monday that this new COVID-19 variant is slightly more deadly to men between 50 and 60 years of age. It's slightly more deadly. And he said that full of conviction. And of course, being a scientist, first of all, everybody was shocked. Oh my God, it's slightly more deadly. And there are two issues, or there is one very obvious issue here. What does he mean by slightly more deadly? Can you be slightly more deadly? You are more deadly or you're not. Slightly is a little bit like somebody saying, I'm slightly pregnant. Can you be slightly pregnant? Can you be slightly more deadly? So I take offense of this slightly. But let's just simply look at it. Is it really more deadly? Because, for example, here, Sir Patrick said, if 1,000 men in their 60s were infected with the old variant, roughly 10 of them would be expected to die. So we have 10 out of 1,000. Whereas it rises to about 13 with the new variant. So 13 out of 1,000. So we can calculate the increase. What's the increase of expected deaths? We would probably say it's a 30% increase. 13 minus 10 divided by 10, that's a 30% increase of dying. My risk, but if I get the new virus, my risk increases by 30%. Right? 30% increase risk from the new variant. Is that something to worry about? A 30% increase. Should I worry? What do you think? Yes. I should absolutely worry about it because my risk goes up. Okay, so we have 10 counts here. That's the old. And the new variant is 13. So that's our sample 1. That's sample 2. What we now want to do is we want to say, is there a difference between these two? And of course, it can come from sampling error, this difference. No, it's a 30%, Jennifer. It's not 0.3, it's a 30% increase. So what we say is, instead of comparing the samples, we calculate the confidence interval for both of these samples, confidence interval 1 and confidence interval 2, because we don't compare the samples directly. Instead, we compare the population that we sort of infer from these confidence intervals. And we say, originally, we believe that the two populations are the same. So that's the first thing. How do we calculate a confidence interval when we have count data? The answer is, this one is a really nasty one, and we cannot directly calculate it, the confidence interval. But luckily there's software out there Let me see if I find the software. There is a fantastic calculator out there, and I will post a link to that. And please bookmark this calculator because you will need to use it. And this calculator calculates the confidence interval for Poisson data, for count data. So here, what you see here is I've got a sample 1 and a sample 2, and I calculate 10 out of 1,000. So what is the confidence interval? Here, the confidence interval goes from 0.005 to 0.02. That's my confidence interval for the variant with 10 per 1,000. Yes, you will get the link, don't worry. For sample 2, the more dangerous one, it's 13, which has now disappeared. I just put that in. Let's not worry about the 1,000. Let's do 10 and 13. So I can calculate my confidence intervals. So if I have 10, the confidence interval would go from 4.8 to 18.4. For sample 2, the really bad one, the confidence interval goes from 6.9 to 22.2. And you see there is an overlap between these two confidence intervals. These are these light bars. Would you say that there is potentially that they are coming from the same sample, from the same population? Well, the confidence intervals, these bars here, overlap quite a lot. And actually, the p-value for that is 0.68. So here, if we draw the confidence intervals, they look pretty much like that. So these two confidence intervals overlap, and the p-value is 0.68. What does this actually mean? We said it is a 68% chance that we make this observation, that we see 10 and 13. So 68% probability to observe 10 and 13 counts if they come from the same population. If they come from the same population, we would see that. Brilliant. Thank you very much, Ed Miller. So P is much higher than our alpha. Alpha in this case is, because we used a 95%, is 5% or 0.05. So we've got 0.68 compared with 0.05. And therefore, we can say the counts of 10 and 13, the difference between them is probably due to sampling error, but it's not very likely that there is an additional factor in it. So 68% means it's the probability that we see these observations if it comes from the same population. And the 68% came from this calculator here that we used. You see this probably here. And it says there's no significant difference. And all I need to do is to put in these numbers of my observations. So I've got 10, and I can do it either by 1,000, and here also per 1,000. And I still get 68%. 68% probability that we see these numbers if they come from the same sample, if they come from the same population. This means the numbers that they have quoted could very easily come from the same population, or in other words, the new variant is no more deadly than the old variant. And of course, yes, I should be worried about COVID, but I should not be worried about this new mutation. And the 95% confidence interval in this calculator, you can choose a confidence interval, but it's by convention, it's usually set to 95%. And here what you see is, here it gives you the confidence interval here for the per 1,000, or you can also do a confidence interval if you're not too worried about 1,000. You just simply say, I look at 1,000 people, 10 will die in one case, and in the other case, 13 will die. And this gives me the confidence interval for a 95 confidence interval. And this is exactly hypothesis testing from A-level. And you are absolutely right. Count data, the Poisson is events per something. Absolutely right. Does that make sense? We will do more on that, but for today, I think I've molested you enough. And all I can say is thank you very much for watching. I will post the link to the calculator because you will need it for some calculations that we are going to do in the future. So, thank you very much, and I wish you all a wonderful afternoon. The dogs are already crossing their legs, so I am going to empty them. Have a lovely afternoon and enjoy. Take care. Bye-bye.